Okay, now that I've run through those housekeeping items, it's time for me to introduce today's speaker. Dilip Molla is a principal consultant with DCM Electrical Consulting Services out of Missouri City, Texas. He received his BSEE degree from West Virginia Institute of Technology, and he's a longtime member of NEC Code-Making Panel 5 and is a key member of NFPA 70E Technical Committee. During the 2012 IEEE Electrical Safety Workshop, Dilip received the IEEE Charles Porteus Steinmetz Award for his dedication to developing safer equipment and promoting safety standards to reduce the number of electrical-related accidents in the workplace. He has experience designing and constructing electrical infrastructure of petrochemical facilities with Union Carbide, and he's employed his safety by design concepts, examining each infrastructure design aspect to maximize safety, which has resulted in many innovations over the years. In 2007, for his extraordinary contributions to the petrochemical industry, he received the coveted David Asbill Award, and today he serves multiple IEEE Standards Association working groups related to the petrochem industry, safety and arc flash hazard analysis, and recommended practices to improve electrical safety. So it's my pleasure now to turn this session over to Dilip and have him present today's topic.
Thanks, Mike. It was a very nice introduction. I appreciate that. Thank you, everybody, for joining the webinar. Today, we'll try to address how you can upgrade your ungrounded electrical distribution system. Some of it may have it. Okay. What were the pros and cons, historical rationale, why people use, we'll cover some of the items, why people use this before, what are the pros and cons of this technology? How do you use insulation monitoring along with it? And comparison of high-resistant ungrounded system. What are the benefits? What are the disadvantages? And how much HRG technology, high-resistant current technology, has advanced over the years. So as we go along, you'll see that we are going item by item. First thing when you design the system grounding decision you have to make, first thing you ask yourself, how important is my service continuity? If power fails, what can happen? Do I create an unsafe condition? Do I create an environmental impact? Then you have to ask, or we used to ask before, are there any line to neutral loads? Because that will decide what you're going to do. Okay? Before the high-resistance grounding technology came in, when I was in the plant engineering and doing the plant work, you only had very few options. You went through this chart and you decided if the system grounding continuity is important, I'm going to go to solid ungrounded, strictly ungrounded. If it's not, okay, I'm going to go solid grounded, because solid grounded essentially will take you down in the first part. Then we ask, are there in line to neutral loads? Because an ungrounded system normally have three-phase, 3 wires and does not supply your neutral load. If the neutral loads are needed, then you select basically solid grounded system. If they are not needed, you select the ungrounded system. This was the chart we went through, and if we have critical processes, then we put a isolation transformer or specialty transformer for single-phase load, and we collected the delta system to design most of our systems. Solid grounded was the last resort, as long as it doesn't affect the continuity. So if process continuity is required, there was only one option at that time, ungrounded system. And what is the ungrounded system? Ungrounded system do not have an intentional connection from the source to the ground. Key part is intentional. Typically it's a 3-wire delta system, delta-delta transformer, or sometimes you can have a 4-wire system where source neutral is not connected, but very unusual. Mostly you see delta-delta. And keep it in mind, the underlying part is the intentional connection. Okay. This is a quote from IEEE Standard Buff Book. You'll see that ungrounded low voltage system apply ground detectors to indicate a ground fault. That's all they can do. They can show whether there is a ground there or not and which phase is ground on. But they do not have any way to locate the ground fault. Only way ground fault could be located on delta system, or still can be located most of the time, except for some technology people claim they can do that, is shutting circuit on and off. So what do you do if you have a delta transformer? You derive a neutral to put a Harrison grounding, and that's what I just wanted to get you aware of this, so we'll keep on, then the technology will follow later on. You can see that you have a delta, you put a zigzag transformer, or some places you put two winding transformers, and you detect when the ground is there. It doesn't tell you where the ground is, it doesn't tell you how to locate it, but it does give you an option to delta, to detect the ground. People who are familiar with 60s and 70s design, and if they're nodding their head, they would have that at their site even current, because transformers, you do not change that frequently. There's another quote from the Buck book, which I hope you can see in the scene. The hardest part is if the ground fault is intermittent. Then the voltage keeps on rising, and that's where the damage occurs. Buck book says it can go as high as 6 to 8 times the phase voltage. I'll show you a schematic in a sketch. Technically, they can go infinite value, but 6 to 8 times some damage will occur and system will shut down. One good thing in electrical system is, and I'm not being sarcastic, all faults are self-clearing. That means anytime a component fails, system will go in a shutdown mode. This happens intermittent ground fault because of the resonance. Then you have a red book, which is designed for power system design. Okay? Normally, the over voltage always degrade the insulation, reduce the life, and most of the time will cause a failure. Insulation system is designed only for certain voltages. After that, for example, 480 volt system will probably fail very soon if you consistently keep on giving it high voltage pulses. And they happen more frequently, failures, than the ungrounded power system, because grounded power systems, whether they're solid grounded or resistance grounded, will tend to clamp the voltage. Ungrounded system does not do that. Okay? In true sense, if there are some electrical engineers in the audience, they will know and they will claim there's nothing in this universe is ungrounded. Electrical system cannot have ungrounded. It's always capacitively coupled to the ground. That's the reason in the second slide I had told you to keep an eye on, intentionally grounded. So every system has a capacitive coupling. That's where the arcing starts. So keep that in mind. There's nothing ungrounded. Ungrounded, when we say, we mean it's not intentionally. But every system in this universe is capacitively coupled. So what happens in an ungrounded system? If there is no return path, the first ground, cable or transformer, it couples to basically to your system. You can see that three-phase system is shown on your front of you, and you have three capacitance coupling to the ground. You have a cable insulation, you have air as a dielectric, and you have ground as a different potential. So basically, in a good system, when there's no ground fault, there's no voltage at all to the ground. Now let's see what happens when there is a ground on it. Okay? When there is a ground fault, the ground cannot go back to the system. There is no return path, but it still builds up a voltage to the ground. And you can see when the A phase is grounded, capacitive coupling will start discharging, and that's where the arcing starts. Ideally, as an electrical engineer, you like to have a bolted fault. Bolted fault is better than arcing fault. And when the arcing fault happens like this, it is showing very minimal current, And that was the reason they were used in the past, because you may have heard the expression, the first fault is free. That means the first fault did not interrupt our system. That was the primary reason in 40s and 50s, before the hydrogen grounding came in, Delta system were so popular, because you could ride out the first fault. System did not shut down automatically. If process continuity was important, you depended on alarm to take the fault off if you could. Now, intermittent fault, they are the most dangerous. One, they are not easily detectable. Second, they keep on raising the voltage. On your sketch, you see a switch which denotes just a modeling. When the switch is open and closed, the ground fault flows. You can imagine the switch is a very high fault system. It is closing and opening very fast, and that's where the arcing starts. How many people who use that Delta ungrounded system probably have insulation failure on motors as well as on your other circuits? This is what tells you how transient overvoltage rises. On the extreme left, you see a system when it's normal. You don't have any voltage to the ground, neutral to the ground. Is going to be very low. If the phase is balanced, you won't have any voltage. As soon as the first fault happens, people believe that that phase goes to ground and it goes to full voltage. That is not true. The vector arrangement changes. If you see, the neutral is elevated. Every half cycle, since the arcing going on, the capacitance restrikes. After half a cycle, you see the neutral elevates even further. This will keep on going on till something fails. Normally, some insulation, either cable or somewhere, will fail to 6 to 8 times and system will shut down. But if it does not fail, it can ignite. If you have 480 volt switchgear on Delta, you may have experience where the switchgear caught on fire because the current did not go to a level to trip the device, but the voltage was striking. We have measured on our sites almost 1200 volts or higher voltage on 480 volt system. It restrikes so much, transient overvoltage. This is a true example. You can see the actual measured dimensions from an automotive facility. Okay. Phase to ground voltage, ungrounded, and then we'll show you high resistance grounded. You can see the pulses. What you see the pulses is basically, if you're familiar with the word high potential test or high pot, that is what's happening to your system. Okay. 120 times a cycle, a second, 120 times a second, it is giving a high voltage pulse, and system is eventually, insulation will fail. Insulation cannot stand that. Common practice used to be use a higher voltage insulation, but that can only delay that failure. It cannot eliminate the failure. And look at that sketch you have, 485 events with over 700 volts. And you can see that if 480 volt system is getting 700 volt peak, what can happen to the insulation? This is the one fault, that insulation failure, that resulted in equipment damage. It was excess of $200,000. And bad part about Delta intermittent voltage is you don't know which part of the equipment will be damaged. For example, on solid grounded, you know where the fault is, only that equipment is affected. Delta system ungrounded, you don't know which part is affected. All of them may be taking an over voltage. So if you use ungrounded, that was the reason we used, because we needed a process continuity. In a petrochemical industry or continuous process industry, an unintentional outage can create an environmental impact, can create a safety impact. So that's the reason Delta system became popular, because it allowed us to sometime to locate the fault if we could by shutting things down, or avoid an outage for a while. And if you can see, only advantage there was process continuity. And that helps us in the safety. We could not locate the ground fault. We could not control the transient overvoltage. Only way to locate the ground fault, as far as we knew at that time on a delta system, was keep on shutting circuits down one by one. With Murphy's law, fault is always going to be on the last circuit you shut down. So basically you had to do all of them. Then some advances came in. Industry response. One was to install insulation monitoring. If direct effect of the delta grounded system is insulation damage, theory was, let's monitor the insulation so we can predict when the failure is going to happen, so we can do something. Next came the technology of high resistance grounding in 60s. How does insulation monitoring system works? Most of the work offline. Some of them will work online. All you do is you monitor the impedance of the circuit, and as soon as the insulation starts failing, it can give you the value that's saying, hey, I am going down below a certain value, and you can do something. You can take a planned outage. The basic philosophy always used to be in the process industry, a planned outage is a lot less expensive, is a lot less troublesome than unplanned outage. So insulation monitoring was the answer that you could take. A planned outage, you could put your program what the insulation should be, and if it goes below a certain value, you sound an alarm. Okay. How do you do that? Since it doesn't have any ground fault path, you need a zero sequence CT. And you need to inject very low frequency current in there, very low voltage, low frequency current. That means when the ground fault, when the insulation damages, that you will have a current in the zero sequence CT. Zero sequence CT is basically, if everything is balanced, it will show you zero, and if there is some current flowing through it, it will give you a value. So as soon as the insulation damage happened, current increased, and it gave you an alarm. But it could not detect the intermittent faults. It does not limit transient overvoltage. And one of the main problems what we found is with this technology was, it was causing a lot of interference with our solid state equipment. Reason for that is, a power system doesn't depend on the ground current. Solid state equipment does. When you inject this current, it ends up in the ground wire, and it may trip your solid state equipment. So we essentially took all the insulation monitoring online off the circuit. You cannot shut the process down. If main goal was to have the process continuity, you cannot introduce a product that will reduce that probability. So now you see we're building up. Ungrounded gave process continuity. So does ungrounded insulation monitoring. Ungrounded system could not locate the ground fault. Ungrounded insulation monitoring gave us a capability that we can locate which system might be affected based on insulation. But still, it does not control the transient overvoltage. So insulation failure is not prevented, it is just predicted when can happen. So you still have to shut the system down. Okay. Then came answer to our problems. High resistance grounded system. It originated in 1960s in petrochemical industry. It was first suggested by General Electric on a paper presented by Duncan Jacobs. And answer was, hey, you can have benefit of both systems. You can have process continuity, and you can reduce the ground fault. Why solid grounded system were not popular? Because the first fault, there will be such high current, they can do tremendous amount of damage, and you shut down. So this was the best of both worlds. You can limit the ground fault. That means on the first ground fault, you can continue operation, and you also limit, it's technically it's grounded. So technically you limit the over voltages and you have flexibility to locate. Then the technology, next slide will show you how we come up with detection schemes. This is a quote from IEEE Red Book, and if you remember, look at the date is 1993, so very old technology. IEEE standards do not move that fast. In 1960, when we introduced this technology in our sites, I say we, I was not the principal designer, I was a user. Red Book, which was the primary document for engineers use for design, first time mentioned that high-resistor grounding has the same advantage as ungrounded system because you can have right through to the first fault. It gives you other advantages. It limits transient over voltage because now the electricity has a reference. IEEE Standard 242, which is a Buck book in 1986, mentioned the same thing. And you look at their wording was different. That's a coordination standard that ungrounded system offered no advantage over high-resistor grounded. Red Book was saying high-resistor grounding is better. Buck book says it two different way. And if you notice, the Buck book is telling you that disadvantaged transient over voltage still stay with the ungrounded system. High-resistor grounding limits that, gives you the ability to locate the first fault, and minimizes burn down. Even the second fault, you won't have a burn down because it'll trip some overcurrent device. Okay? And that's the reason Buck book in 1986 recommended. For these reasons, they are being used less frequently, they being ungrounded system than high-resistor grounded systems. Where are we? What are some of the advantages of high-resistor grounding? First, if you recall, I told you the delta system is there is no ground return path. High-resistor grounding gave us a method to have a return path. So if you have a ground fault, you could locate it. How did technology came about locating? When I say we did that, don't take it to mean that I designed it. I'm just a practitioner. It was technology was built that since the current is so low, sometimes it's about 1 amp to 5 amps, normally more close to 1 to 2 amps, it was very hard to detect. So a pulsing contactor came in. All pulsing contactor does, it gives you 40 pulses per minute. And you can check the pulsing current, where is it going. Contactor shorts out part of it, or you can have multiple resistors. That technology is one of the other. Technically, what I'm aware of, you have 5 resistors in there. Then when you want to pulse it, you only have less in circuit to give you a higher current. And that's how the detection scheme came in. That was a very important tool for operating engineers. Now we could make an effort to avoid a second ground fault without shutting down like we used to do on Delta. Okay. How do you locate that? It's basically we're locating the pulsing. What you see on your screen is an instrument called Rogowski coil. If anybody from Polish origin is there, I'm sure they'll correct me like my friend Mark Zawadzki does. It's a Rogowski, not Rogowski like we say. But anyway, all it does, it's a zero sequence CT and tells you what the current is flowing through it. So what you do, you identify which circuit it is, you keep on going along with it, and if you notice on the right hand side, when you go past the fault, current will disappear. All you're looking for in ammeter is a pulse. Actual measuring quantity is not important. As long as the needle is pulsing, you know the ground fault is there. Now the same study that you saw that, now see the difference. After they installed the high resistance grounding, before they were 400 watt, peak events over 700 volts. Okay. After that, high resistance grounding, they were 0 over 700 volts. Peak voltage 660 volts is because of the pulsing when it goes on, it records as an intermittent fault. That's the reason peak voltage was 660 volts. If it didn't have to pulse it, it would not have any over voltage at all. Okay? And other thing you notice that on a peak voltage was, in certain cases, 1050 volts, ungrounded system. A cable that you have is rated for 600 volts at max, used at 480 volt. In 1000 volts, if you consistently give it a such kind of transients, it's going to eventually fail. Now, cable failure was less damaging than the motor failure, because cable failure we could repair. Motor failure we could not repair without replacing. So, high resistance grounding relieved that problem for us. So now you had ungrounded system that gave process continuity. That was the driver. But it could not give ground fault location, could not give transient over voltage. Then came insulation monitoring. It gave 2 out of 3. It gave process continuity and locate ground fault. But insulation damage was still happening. That's the reason high-pot became very popular. With high resistance grounding, now you could continue the process. You could locate the ground fault, and you have a mechanism to control transient or voltage. So it gave all 3 things we wanted. That's the reason it became so common and popular. Some other reasons, excuses or reason, whatever you call it, I just don't have room. My system is so compact, I can't put resistor anywhere. I'm worried about if I lose the resistor circuit and I won't know. What do? I don't have time to locate the ground fault even with pulsing system. Okay? I don't have people. I don't have time. What if I don't want the fault to stay on the system indefinitely till I detect it? Is there a method available? They'll take it out within a certain time. And what if the fault is intermittent? People who are listening and say that, hey, you say that intermittent fault is a dangerous one. How does high resistance grounding prevent me from that? And what if a second fault happens? When second fault happens, if the first fault is not cleared, you will have face-to-face fault. The system will trip. And last thing was, my budget can't afford it right now. I just don't have money to spend on these things. So let's see if we can answer one by one. First, I don't have enough room. On the right-hand side, you see a outdoor enclosure, NEMA 3R, and you can see the dimensions in there. It has 14.5 by 11 inch by 18 inches high. If you look at the bottom of the screen and the enclosure, you'll see a zigzag grounding transformer. So all you have to do is put this close to transformer. If you have oil-filled transformer, normally you have a lot of room. You can put on the top of it. You can put on the side of it. You can put inside. So room is not a concern. It's very easy to convert delta system to high resistance grounding systems. Second question was, what if I lose the resistor circuit? I'll be back to delta system without realizing what is happening. And industry always responds to needs. Industry responded, and one supplier has, I-Gard does have, I know, I'm sure others may have it too, maybe, is a sensing resistor. It's a very high impedance resistor, and that resistor monitoring relay you see, it is closed, so very low current is going through sensing resistor. If the main resistor fails, the current goes up in a sensing resistor and gives you an alarm. So you can now detect when the circuit is open. Ideally, you want to check this before you commission the system. So with this circuit, you have, as long as Control power is available in the relay circuit. You don't need main power on, so you can check if the circuit integrity is okay before you commission. Most of the system available in the market is you can only check when the fault happens and it didn't clear. So this gives you one option. Now you have protection against resistor circuit. Now there are people saying, okay, it gives me alarm. I still have to shut down because I'm working ungrounded. My process is too important. I don't want to shut down. Industry responded by having two resistors in parallel. Both work continuously. If one of them fails, resistance goes down and resistance goes up, and your current goes down and you can alarm it. That way you can know which resistor has gone down and which one is still working, but now you have time to have resistor repair during planned outage. You can have a sophisticated system where you have a disconnect. Some of our sites have that, where you have disconnect that we can disconnect that faulty resistor and try to put a new one in there without shutting down the system. You can still see the incentive is still the same, process continuity. Now Harrison grounding it allowed us process continuity to do it safely. That objective has not changed, to keep the electricity going so we can have some process continuity in there. Next is, it takes too long to find the fault. I cannot do like that. I don't have time to take a pulsing detector and go along the cable or somewhere and find equipment. Of course, industry obviously responded that you have the relays with zero sequence CTs which will automatically detect which phase has faulted, which feeder has faulted. Now, depending on your hardware you have, if your feeder has multiple MCCs, you may still have to go and see which MCC motor control center may be faulted, but at least you know which feeder it is. Of course, if your process is very critical, you may have on individual motor control centers. When we do our safety systems, we will have on every equipment that can affect the safety system a ground fault monitor. Tell us exactly which is, so we'll have a backup. So you can see industry has responded to needs, whichever way you need. That is an excellent system for you to save time if you don't have time to detect or don't have manpower. Then was, I don't want the fault to stay on the system indefinitely. This is in worse way of saying I don't trust my people. They won't clear the fault. Second fault happens, then no, system will come down anyway. So now you can have a timer. In some of our remote locations, we do have a timer that we give people 8 hours. By the time alarm comes, if you don't clear, system will shut down, or 1 hour or 2 hours, whichever time you decide. So you have an option to customize this Harrison grounding available options to meet your needs. If people want, for example, if you have fault on Friday and you don't want to last till Monday, you tell operators, hey, you have 1 hour to clear, find which equipment is faulty, and after that we'll shut you down. We don't want second fault. What if the fault is intermittent? Harrison grounding normally may not catch it because it depends on picking up a relay. But now the latch relays are available. They will catch that intermittent fault and tell you there was a fault in the system, even though 480 volt fault system will clear. 480, 600 volt faults will clear. Medium voltage will run into face-to-face fault if not cleared, but 480 volt fault will blow out. And so this gives you an option. Hey, the fault did happen. We need to take a planned outage and start checking. And all of this system can go now to a data logging, so you have time and everything available. What if a second ground fault happens? Second ground fault happens. Now you're going to go face-to-face. I don't know how many of you who are listening had responsibility for the plants. I had few plants under my responsibility. I was technologist, and one of my main fear was, for some reason, most of the ground fault happens Friday after 5 o'clock when we don't have anybody to troubleshoot. And you are waiting till Monday with your fingers crossed. I hope second fault does not happen. Industry responded. That was a godsend thing to us. I wish it was there when I was being an operating engineer. You can put prioritizing system. It tells you that which feeder has fault. If you imagine that you have 50 feeders or 20 in a typical switchgear, and first fault happens in unit 5, now you can prioritize that, hey, unit 5 is only priority 3 for me. If a fault happens in unit 4, which is a higher priority, you said, okay, I'll take the number 5 down. For example, how we use that technology, lube oil. We need to keep it going for generator. That'll be always the highest priority. That if next fault happens, take it down, keep my lube oil going. So this is a very important technology. If you're designing your new system, I'll strongly encourage you to consider this second fault isolation system that you can prioritize and buy you some time. One question was, I can't afford it. Look at the industry losses that happen due to electrical faults. This came through NFPA and insurance industries. We don't know exactly which industry might be, but petrochem is one of it. You can see the average loss is $769,000. You have to ask yourself and ask your management, if you can't afford high-resistance grounding, can you afford this? Can you afford to take a $700,000 average loss plus other problems? This is just economic loss. Sometimes system interruption has environmental impact. That is the petrochemical industry mostly concerned about. The environmental impact. Some gases will be released. So consider that. Then you ask yourself, can I afford not to have high-resistance grounding? Now you can see that process continuity, which was our main objective, is maintained in all 4 cases. Whether you have ungrounded system, you supplement with insulation monitoring, or high-resistance grounding system, or advanced high-resistance grounding, which has second fault protection. Of course, locating ground fault was not available in ungrounded, so that falls off the wayside. If you are concerned about equipment damage, which you should be, because current equipment is very custom designed. Older equipment always had insulation margin, and there are some manufacturers, I'm sure, listening, and they will know that now there's not that much insulation margin is left due to cost pressures. So it gives you, high-resistance grounding gives you over-voltage protection. Other you see it minimizes arc flash. How does it do that? High-resistance grounding is the only one to do that because first fault is going to be less than 5 amps. You do not have any arcing in there. You can detect it. If you have a second fault protection system, you can detect it and remove it. Would it reduce the incident energy? Absolutely not. Would it reduce the risk of arc flash? Absolutely yes. Then you have capability to latch on intermittent faults. You don't have people. People are getting very priceless commodity you can afford. You can have a feeder indication that tells you which feeder it is. If you are concerned about resistor monitoring, that you don't take routine outages, you can have online monitoring. So you can build your system based on your needs, what you need. I mentioned that it mitigates that arc flash. It reduces the risk It doesn't reduce the incident energy if the face-to-face fault happens. How can we say that? Industry data indicates that 90 to 98% of all electrical faults start at face-to-ground fault. If they are not cleared, then they go into face-to-face fault condition. If you can limit the ground fault to a low level, say 10 amperes or less, probability is very low, it will go to face-to-face. If you have a solid grounded system, the first fault will have a 20,000 amp or 10,000 amp fault. That fault will quickly go to face-to-face if it's not clear. So that's where we can say it reduces that arc flash risk. It doesn't reduce that if three-phase bolted fault happens, it's not going to reduce, but three-phase bolted faults are absolutely very rare, mostly because of that your human error or something like that happens. In my 40 plus years of experience, I've only found 4 cases of bolted fault. And unfortunately, all the places were where we left the jumpers on after the testing. We didn't remove the grounding jumpers. So that's why Dunkey Jacobs' book says, and 70E also will tell you, that it will mitigate the risk. Right? Now, what were our options before? When I started designing system, you only have few options. If your process continuity was important, use ungrounded system. Okay? If your process continuity not important, use solid grounded. All of a sudden, Higher grounding came in. Now there is no need to have ungrounded system. If your process continuity is important, you go to advanced higher grounding. So you have all the options that you can pick up. Automatic detection, second fault priority. Okay? If you're concerned about arc flash, answer is go to higher grounding system. When you go to advanced, you can get a second fault priority, and you can see the risk analysis, how does it reduce. If most of the fault, 90 to 98% first faults are ground faults, and if you remove that fault, the probability further goes down, that second fault will happen at the same time. Now, nobody can tell you it will be 100% effective. There's no 100% probability. But with second fault priority, it's pretty close unless there is a human error. If your process continuity is not important and you don't care about arc flash, of course, solid ground is still an option. Now this is a built up on that. What if you say that one of the disadvantage of higher grounding is you cannot use phase to neutral load. So if your question is, what if I do have? My system is not that clear. So you still use critical process, you use higher grounding system, but for single phase loads, you put a smaller transformer. When I go to audits in the sites, I'm so scared to see for electricians that they are using 277 480 volt lighting or 120 208 lighting with it coming from the main transformer. You can imagine 120 208 if it's coming from main transformer, just for discussion's sake, if it's 1000 kVA, you have close to 30,000 amp fault. If an arc flash happens, you're going to have a tremendous arc flash. Now if you have a higher grounding system and you use a 30 kVA transformer, for example, for lighting, you can see you're making systems safer by design. One of the concepts all designers should employ or do employ is system safety by design. So you cut down the potential. So you can use higher grounding for critical processes and then use smaller transformer for your lighting or other you may have single phase load. If you're concerned about arc flash, and who shouldn't be, arc flash is a very dangerous condition that basically, like the name implies, it burns people. So you use advanced higher grounding system. you take the second fault out. When you do risk analysis, you can tell your management that, hey, if the first ground fault is 90 to 98% and I don't have a ground fault, I have a second priority system. Now, what is the probability I'll have two faults at the same time? It is there, but it's very low. So you can see HRG, high-resistance grounding technology, is an option. You can use it. We have used successfully since 1960 up to 5,000 volts without any problem. In one of our international plants, you use up to 6,900 volts. Next one. Okay. This is a Buckbook quote again. And this 2001 version, you can see we are learning. I'm also part of Buckbook. High-resistance grounding helps ensure a ground fault of known magnitude. Now I know wherever my resistor is set, 1 amp or 2 amp, depending on the charging current, that's the current I have to handle. And if you look at the last sentence, this makes it possible to identify the faulted feeder with sensitive ground fault relays. You can use pulsing, or the relay I showed you with the zero sequence CTs will probably detect that for you. Red Book is still 1993, is being revised right now, and you saw that quote before. High-resistance grounding provides the same advantages as ungrounded system and more, yet limits the steady state. So it has the same benefits as ungrounded, but without the disadvantage of ungrounded. So there is no arc flash hazard in the first ground fault because the first fault is very low magnitude and you can always detect it. So high-resistance grounding is the preferred method over ungrounded system. This is again Buckbook, 1986. Ungrounded system offer no advantage. So if you have that, it's very easy to convert. It's no effect on the process as opposed to solid grounded system. You can very easily convert it and get the advantages, control the transient over voltages, detect the first fault if you can, and minimize the equipment damage. Thank you very much, and now I think we're ready for your questions. Go ahead and ask your questions, send it to the website.
All right, thank you, Dilip. That was a very, very good overview of different types of grounding systems and their advantages and disadvantages. Before we jump into the Q&A session, please take a moment to answer the feedback form that's going to appear on your screen now. If you have pop-up blocker technology enabled, you're going to have to disable it for a moment so that you can receive the form. The other note I want to make is that I-Gard will be sending you a copy of the presentation in a PDF format after we close the event, so be on the lookout for that. All right, so we'll move into the questions here, and the first one we're going to throw your way is there a general rule to size a zigzag transformer for converting ungrounded to an HRG system? And also, is there some rule of thumb to size the overcurrent protection for the zigzag transformer?
Okay, first thing for zigzag transformer, that depends on equipment design. My best suggestion to you is to let the manufacturer know what transformer size you have and what your distribution system, and they're the best qualified to design the system for you. If you design it, you will probably over-design, but it is going to take very low current in the sense, so you don't need to over-design that. Only time you need it when the fault happens. So my suggestion to you best is to do that, is let that manufacturer, the equipment supplier, design it for you. And next question was what, the overcurrent protection?
Yes.
Okay. Overcurrent protection on high-resistance grounding, you don't need on first phase to ground fault. But other than that, you don't have any difference what you use because next fault is going to be phase to phase. So overcurrent protection does not change. If the risk changes, reduced drastically on the first ground fault. Okay?
All righty. Next question, can high resistance grounding be used with a main tie main switchgear lineup, do you need multiple resistors for this kind of arrangement?
Okay. Again, one of my favorite answers is it depends. If you're working as a closed tie operation, you may not need it. If you like to keep your flexibility that you want to work with the open tie, then you do. So it'll depend on your system and your design that what you do. But considering high-resistance grounding is always preferable to have a self-contained system for each bus, so you can maintain one bus without other, or you can operate with a tie breaker open. So they'll depend on your system.
Okay, great advice. Of course, arc flash is top of mind with many folks, and this question focuses on that issue. Philippe, they'd like you to explain why you have less chance of an arc flash with a high-resistance grounded system versus a grounded system.
Okay. Now, let's go back to the presentation where I mentioned to you 90 to 98% of the faults starts at phase to ground. In a solid grounded system, phase to ground, you will have full short circuit. Arc flash is proportional to current time clearing time multiplied by clearing. Since the current is so high, you will have a very high arc flash. NFPA 70 also tells you that why high-resistance grounding mitigates the risk, because the first fault is going to be less than 5 amps. 5 amp would not have an arc. So it would not have an arc flash. But of course, arc flash is calculated based on 3-phase voltage fault. So I would not tell you the arc flash is reduced. I'll tell you the risk of arc flash injury is reduced. There's a difference. Okay? If unfortunately you have a 3-phase voltage fault, somebody forgot the jumpers off, then you have the same problem. But if you have a second priority system, if the probability of the first fault is 90 to 98% ground fault, and if the second you clear that, next fault the same probability happens, 90 to 98%. That's how HRG reduces the risk of arc flash. NFPA 70 in 2012, even 2009 was very clear that this is one of the methods to reduce risk of arc flash injury.
Great clarification. Appreciate that. Our next question is asking about ratings. What should the insulation rating of the conductor be between the neutral point of the transformer and the NGR on a 4160/2400 volt system?
Okay, if you look at 25186 in National Electrical Code, it very clearly says it should be full system voltage rated. It should be 2400 volt because that's the maximum voltage you're going to get on it. Neutral point of transformer to the NGR. Okay, now if you, unfortunately, 2400 volt cables are no longer that readily available, so you might end up using 4160, but you can always look at 25186 of National Electrical Code. It will give you very specific direction that what the insulation rating should be.
Okay. Moving on to the next one here. Is there any safety issues with connecting line to neutral loads on HRG systems?
Okay. That's a very different question to answer. If you look at safety, probably no, because system won't work. If your system is set at, now Canadian electrical codes I understand in certain cases allow, but Article 250.36 of National Electrical Code prohibits line to neutral load, because you can see the principle is that you're depending on if as soon as the current flows, you have an alarm indication. If you use line to neutral load, there will be always neutral load flowing through the circuit, and you will have a alarm condition all the time. Answer is you should not be using line to neutral load with high-resistance grounding unless you put a step-down transformer.
All right. It looks we're getting close to our time. I'm probably going to go about 5 minutes over, so I'd just like the audience members to know that. Instead of ending right at 2 o'clock, we'll probably extend it to about 2:05. We've got quite a few questions that are rolling in right now, and we're trying our best to prioritize them and get those answers out to you. All right, Dilip, here's the next one. Is there any safety issues with connecting line to neutral loads on HRG systems?
I thought we just addressed that, didn't we? That was the last question, I believe.
Oh, I'm sorry about that. Let me get back on track here. Thank you. Okay, can we install HRG on a generator?
You definitely can. In fact, on large generators, HRGs are recommended. If you look at that 13.8 kV generators or higher generator, what does HRG do? You would not keep it running, you will trip it, and keep that in mind. If a solid grounded generator, the first fault in the winding, it may carry very high current. That means winding will be definitely damaged. When you have a HRG system, very low current flows in there, alarm will be coming on, you can still shut down the generator, but now it's very easily repairable. If you can detect the fault, it's repairable. So yes, you can use on a generator. Now, on 480 volt, you have to look at your system. If system is connected to utility, you may not be able to use it. So HRG is a system design, is not a component design.
Okay, great. As all of us know, data center work has blossomed in recent years. So this question focuses in that arena of the market. Does anyone use HRG in a critical data center application that you're aware of?
Okay. Most of the petrochem industry, at least what I'm aware of, will use HRG to power supply to critical data center. Of course, we have a double redundancy or triple redundancy also, but it's good to have HRG. In fact, anywhere a process interruption can cause you problems, HRG is a preferred option. It doesn't matter it's a data center. It doesn't matter it's a control room in an industrial facility. Anywhere process continuity is important and loss of power can cause you economic loss, you need to do that.
Okay, good point. This one deals with the HRG system again in reference to a specific component, and the person is interested in wondering how well it works with VFDs.
Okay. Before I answer the question, somebody just passed me a note. I have people here, and they're saying that Yahoo, Apple, and U.S. Bank in their data center do use high-resistance grounding system. Okay.
Okay.
Now let's answer the next question. Do they work well with that variable frequency drive? They work very well as long as system is designed. Variable frequency drive manufacturer has to be told before they quote the system and supply you the system that it's a high-resistance grounding system. Main reason is when you have a solid grounded system, the maximum voltage in the component is phase to neutral. If you have a high-resistance grounding system and you let the first fault while you're clearing the fault go on, you have phase-to-phase system and VFD component will be damaged. In fact, most of the large user, at least the paper mills are very large user of VFD. They specify VFD system on HRG system with all their VFDs.
Okay. We've heard some benefits that you've described for working with HRG systems. This person's interested to know, is low resistance grounding better than high resistance grounding? Okay.
Again, it depends. Now, on a medium voltage system, especially 13.8 kV, the charging current is so high that you cannot size the resistor and continue the fault. Keep that in mind. High-resistance grounding commonly understood to mean that you can continue the operation. In low resistance, you cannot continue the operation. It will limit the arc flash, definitely. It will isolate, but it will give you very high current, but you cannot continue. So if your main requirement is process continuation, then high-resistance grounding you need to use. If that is not a concern, on a lot of people I know in industry, even 4160, they use low resistance grounding. That is their privilege. High resistance grounding can work, but either system will work. Highest and grounding is preferred because it gives you lower current value. But sometimes highest and grounding would not work. Charging current is so high that if you have a 50 amp charging current, you don't want the fault to persist. Can you use highest and grounding? Yes, you can. You may have to trip it based on a fault like we do on 13.8 kV generators.
Okay, part of the issue that comes up when discussing these different systems, obviously, is how do you make a step to get into it? How do you begin your upgrade? So this question focuses on, we plan to keep our ungrounded system, and they say due to special needs, but what is the best first step to upgrade it? And I assume they mean upgrade to maybe start to move into the possibility of having it on a high-resistance grounded setup.
Yeah, the best method is, since it's being sponsored by I-Gard, I should tell you, call I-Gard, is that you can, all you need, if you remember I showed you the cabinet, you have to look at that your system, and all you have to install a highest and grounding system that will convert your delta to highest and grounding, and it's a very simple process. It is not a complicated process. Of course, it'll depend on what options you want. Do you want second fault priority system? Do you want instant isolation? Do you want a timer? But converting from delta to highest and grounding is a very simple process. All you have to do is call a qualified supplier or a consulting engineer, and they can probably go step by step with you.
Okay, good advice there. All right, this will be our last question because we're getting close to my 5 minutes after the hour here. This person references working with a utility where they may be in control and kind of create a situation where it says the utility will not unbond the primary neutral from the customer neutral. So how can a high-resistance ground be used? Is an isolated neutral required in this circumstance?
Okay, if you have primary and secondary bonded together, there is no practical way to use highest and grounding. But you have to ask utilities why they are doing this. If you're a large user, we have been always be able to convince them that give us 2-winding transformer, primary belongs to you, secondary belongs to us. If you're a small user, you may have that problem. Now, what is utilities' concern? Utilities' main concern, and that is not valid. If some utility people are here, I would like to address them. The concern utility people have expressed that when you ground the secondary, the ground currents can flow through the primary side. That doesn't happen. So best you can do is you have to convince utility to unbond primary and secondary. If they don't do that, it's a very complicated process to do. Then you'll have to put another transformer to isolation one-on-one transformer to come out with a highest and grounding.
Okay, good tips there. All right, well, I'm afraid we've run out of time. On behalf of EC&M, I'd like to thank I-Gard for making today's webinar possible. I'd also like to thank Dilip for pulling together all this information and really giving us a great overview on the different types of grounding systems that they currently have, what you might be able to move to, the advantages and the disadvantages of all those different types of systems. Wonderful job, Dilip. And as for our audience members, we look forward to hosting you all at a future EC&M event. So enjoy the remainder of the day, everyone.